lesson is on systems of equations. And what systems of equations is looking at equations that use the same variables. So just like the equations that we've been graphing with the x and the y, and using slope-intercept form where it's y equals mx plus b, we can look to see where those two or more equations intersect. And that intersecting point, that would represent the solution. So here's an example of a system of equations. The first equation is y equals x plus 9. The second green equation is x plus 3y equals 15. And you can see that when you graph them, the solution is this ordered pair right here, which is the ordered pair -3, 6. So this ordered pair, -3, 6, would be the solution to both of those equations. There are different types of systems of equations. So the example we just looked at is one where it is one solution. So when the systems of equations where they intersect, that is the solution. There's 1 point for a solution. Another option would be if it's 0 solutions. So if you look at these two lines are parallel. They will never ever intersect. That is why it is 0 solutions. There's no point at which those two lines are going to ever cross. And the last example is infinite solutions. So it's hard to see because they don't actually show you both lines, but you can see two different equations here. Y equals 1/2 x plus 3 and -x plus 2y equals 6. Both of these equations, when graphed, formed this exact same line. So this means every single infinite point on this line is a solution. So that's why we say it's infinite solutions, because there's an infinite number of possibilities that would be a solution to that systems of equations. So these are the only three options you can have for solutions. You can have one solution where they cross at 1 point. You can have 0 solutions where the two lines are actually parallel, and you can have infinite solutions where the two lines are actually the exact same line that are graphed. So to find the solution of a systems of equations, you can graph the equations in slope-intercept form. So in this first example, I have y equals 2x plus 2. So I know this equation is crossing at the y-axis at 2 because the y-intercept is 2. So that makes this the ordered pair right there. And then the slope is 2, so I would count up 1, 2 to the right 1 to get to my second point. And you can connect those two coordinates on your graph. Next point, I'm going to change my color so you can see the different graphs. So the next one here is the equation y equals x minus 1. So my y-intercept is at a -1. So here's the 0 for origin at -1 is right here. And it has a slope of, there's no number here, so I know that's a slope of 1. Think of it as 1 over 1 for your slope. So up 1 to the right 1 gets me this ordered pair here, that point. So now when you connect your 2 points, we should be able to see where these two equations cross. The point is a little bit crooked here. But you can see that these two equations cross at this point right here. This is the ordered pair -3, -4. So if we check this, if we check that our solution is -3, -4, and you want to check to make sure it is correct, you can plug it back into each equation. So y equals 2x plus 2. If I plug in -3 for x and -4 for y, we would end up with -4 equals 2 times a -3 plus 2. -4 equals a -6 plus 2. And -4 equals -4. So that one checked out for that equation. So now it's important to check for our other equation, y equals x minus 1 plugging in -3 for x and -4 for y. So -4 equals a -3 minus 1, and -3 minus 1 does equal a -4, so it checked out. So this is our correct solution. -3, -4 is a solution to this systems of equations. If we try another pair of equations, so again, graphing using slope-intercept form. In this equation, I can see it's crossing my y-axis at 2. So up 1, 2. Here's our first point on this top equation, and it has a slope of a -3. So that's a rise of a -3, a run of 1. So down 1, 2, 3, to the right 1 gets me right here. So here is the graph. I'm going to make it a brighter color so you can see the line. Whoops. To graph this, so crossing between those 2 points. And so now graphing our second line, it's crossing at my y-axis at a -3. So down 1, 2, 3, and has a slope of 2. So up 2 to the right 1. Here's the solution. It actually hits our other line, the other ordered pair that we found. So if we graph that one, connecting between those 2 points, you can see the solution to this systems of equations right here, the ordered pair 1, 1. Because you can see right here where they're crossing, or 1, -1. To the right 1, down 1 is 1, -1. So again, if you check your answers back into the equations, it should be correct for both of them. It's important to go back through and do the check, plugging in 1 for x and -1 in for y. So 3 times 1 is a -3. -3 plus 2, that equals -1, and that's what we should have it equal to. The second one, 2 times 1 is 2. 2 minus 3 is -1, and that is what it should equal, is -1. So the next part of the lesson is talking about classifying the systems of equations. So make sure you have this written down in your notes. For classifying, they explain consistent equations is if there is at least one solution. So the two graphs that we just did, the two equations we just graphed, those are both consistent because they had at least one solution. They're independent if it is exactly one solution. So the two graphs we just did are also independent because there is exactly one. And dependent means there's an infinite number of solutions, meaning the two lines that you graph are the exact same equation. And they also call this coincident, that the two lines coincide within each other. They're the exact same lines. And the last one, inconsistent, means there's no solution to the two systems of equations. So that means they're actually parallel lines. So to practice graphing these equations, the top two represent the two equations that we just graphed. So this one here, there's at least one solution, and there's exactly one. So we would label that as consistent and independent because there's at least one and there's exactly one. So consistent, independent for the first one. And the second one is just like the graph that we just did, where our solution was 1, -1. There's at least one solution, so we know it's consistent. And there's exactly one solution because they cross only at one point, so we know it's also independent. This next one, there's not at least one solution because they don't ever cross. These two are actually parallel lines. And they're not independent because there's not exactly one solution. So if you go back to your list, the one where it's parallel lines was inconsistent. Parallel lines means they never cross, so we would label this one as inconsistent. And I'm fine if you use your notes with this. If you can't remember which term goes with which, go ahead and use your notes. And this last one, it's a little hard to see, but here's one equation here, x plus y equals 2. Here's our second equation, 2x plus 2y equals 4. So think about what the different terms were. Consistent means there's at least one solution. So when I look at these two lines, they overlap. There is at least one solution because they're identical equations when graphed. So we know for sure it's consistent because there's at least one. Is there exactly one? No, because they're the exact same lines. There's infinite solutions on here. So the other one we want to use is dependent. So it's dependent, and they also call that coincident. So there's actually 3 words you can use with this. Dependent, because it's infinite solutions, and you'd also call it coincident because they're the exact same line.